of experiments, and I suggest it's time to start. Jarek, do you agree?
Yes, you can start every time. Yes, we'll do discussion.
Okay.
Sure, yes.
So I put to full screen mode, and yeah, for Mark's comment, I will try to focus on this question.
No, I came for the experimental. Let's go very, very slowly, specifically at the E-15, right? Because that's where nobody agrees in the Zitterbewegung world.
Okay. Okay, so we start. Welcome to my presentation. I will present a particle model that is based on direct interpretation of Compton scattering measurements and gamma spectrum measurements. So my talk today will be very experimentally oriented, and thank you for the audience who are interested in the hearing the most simple interpretation of what measurements tell us. Now, this work that I will present today is not only my work, but I have the listed co-authors who have been very much helping me with both experiments and measurements. Now, the model which I will present is different than other models in the literature, and in the end, it seems to me that the difference comes down to what physics means to different people. So these days, for various people, physics means various meanings, and it's okay. Let's just make sure we understand what we mean by physics, and especially in the context of this presentation. So our methodology is the following. For us, physics is an experimental science. So it means that we do not make any hypothesis without direct experimental evidence. So, for example, we do not imagine 80 giga-electron volt particles flying out during neutron decay because there is no experimental evidence for that. Also, we are interested in any experimental counter-evidences. So we can discuss it also during the question session. If you have any idea of counter evidences to what I present, I'm very interested to hear. I do not want skeletons in the closet. Second point is that we apply Occam's principle. For any observation, there are many alternative ways how we interpret it, and interpretation of experiments is always somewhat subjective, and we aim to choose the simplest explanation among alternative ones. This is Occam's razor. The risk is to oversimplify a physical model. So how do we know we are not oversimplifying? As long as the model gives a good match with experimental data and has predictive power, it's not oversimplification. So important is to have in the end some kind of formulas that give us predictive powers. Third important point is that we do not violate any foundational physics laws. So, I have, during my high school and university studies, I put a lot of effort into learning the foundations of physics, all those laws that genius people before us laid down. And, I do not like when somebody just blows up the foundations. So in particular, we do not violate Maxwell's equation, which means we do not leave any field energy uncounted. We do not violate Noether's theorem, which means we do not have virtual particles just randomly violating energy momentum conservation. And also, we do not violate the Klein-Nishina law, which means that we take Compton scattering data seriously. We do not give any exception to quarks or virtual quarks. Okay, so I think that's acceptable and reasonable to say that we have a physics foundations that are well tested. Engineers are using it. So if engineers are using these laws, we should not just blow them up and leave anything uncounted. Also, we apply these laws consistently on all the distance scales. So we do apply Maxwell's equation and also general relativity, both on macroscopic and microscopic distance scales. And yeah, I had some discussion with proponents of different theory who who say that well, this is not reasonable because we know that Maxwell's equation and general relativity does not work on the microscopic scale. And then I was surprised. Okay, I don't know who knows this. I do not know about it. In fact, during my studies, I studied the Dirac equation, and as far as I know, Dirac equation is a relativistic equation, and Dirac equation does include electromagnetic potential term. So if somebody does not want to throw out Dirac equation, there is no basis to claim that Maxwell's equation or general relativity doesn't work on the microscopic distance scale. Like, this is one of the claims that I really faced. But I think we can agree that if the Dirac equation is considered as a successful equation, in the end, it's one of the most precise description of the microscopic phenomena. Then the Dirac equation does reflect that general relativity and electromagnetism indeed works on the atomic scale as well, and we can be happy that we can apply foundational physics laws on all the distance scales as far as we know. Okay, so these are the principles that somehow define our thinking and the way we approach to explore particle physics. Now, let's see how to apply these principles. And we start with the electron as the best studied particle. And in particular, we consider what happens during electron light scattering. So it means that there is an incoming photon that interacts with the electron recoils into some direction, and a photon of different wavelengths goes into other direction. Now, the way this fundamental light electron scattering works depends on the energy of the photon relative to the electron mass. So there is the low energy limit. It's called the Thomson limit. That's when you have Thomson scattering. And there is a high energy limit when photon energy is much higher than electron mass. And this is called the Compton scattering region. So in this case, the scattering process is Compton scattering, and this cross-section is described by the Klein-Nishina formula. So here you can see the scattering cross-section going down with the photon energy. And in the Klein-Nishina formula, you have the spherical charge radius of the electron appearing. And when you match experimental data to the formula, then you can measure or extract the spherical charge radius of the electron. And by taking the scattering data at its face value, you see that the scattering radius that you measure is 2.82 femtometers, which is exactly the so-called classical electron radius. So it has a name because it appears in other contexts as well. Now, there is something very special about this 2.82 femtometer value. So to find out what's special, let's calculate what is the electric field energy down to this radius. So here is the formula. This is a direct application of Maxwell equation. So well-known formula of calculating the field energy from infinity down to this spherical charge radius. When you do this integration, then what you find is that the electric field energy around this radius value is 255.5 kiloelectron volt. It's exactly half of the electron mass. So in this way, the Compton scattering measurement tells us that half of the electron mass is electric field energy. That's a direct interpretation. Now, if half of it is electric field energy, perhaps the other half is magnetic field energy.
Hey, Andras, is it okay if we ask questions during the presentation?
Short questions. Yeah, you can ask a short question and then longer ones, let's leave to the end.
Sure,
So please go ahead.
Okay, thank you.
Yeah.
So This part is very important to me because we need to know that it is actually an observe. And pardon my ignorance, but when I chat GPT the whole thing, because that's how I go about my research, I could not find any direct evidence for the 282 femtometers. It probably missed it. This is ChatGPT. It's not perfect. But it did nail the classical radius as, again, the definition of the R0 for which the electromagnetic energy matches the mass energy. So in this narrative, there is no surprise. It's actually the definition of it.
Yeah,
which is
except that the definition leaves out the half parameter, because if you integrate electric field energy down to this classic electron radius, you get only half of the electron mass, not the full electron mass.
Right. Sorry. Yes, the half. So do you have it in writing, this Klein-Nishina derivation of the 282? Is that something that you're absolutely certain? Because that's, to me, is the whole reason I'm here, like that this 282 femtometer is observed and not just a formula number that says the radius equivalence would be blah, blah, blah.
No, it is. So here you do see the cross section, the scattering cross section. So what?
So this is the scattering cross section. I can't see. My screen is too small. I apologize. What's in Y?
Yeah, so it's measured in Barnes unit. So when you have
section.
so when you have the photon energy in the 1 to 10 mega electron volt range, then this scattering cross section is the range of millibarns, and you can map. So there is a range of measurements. So this scattering cross section has been quite precisely measured for a wide range of photon energies, and in that sense, you can match the Klein-Nishina formula to very precisely measured data, and from that you can extract this spherical charge radius.
I'm going to stop bothering you in 20 seconds, but for the paper for the papers we're writing for entropy, I would love to have that in writing. Like, this is the Klein-Nishina formula, because to me that's the key point. If in fact this integral, reflects a real physical sphere, then that's super interesting, and that's a really solid starting point for everything else. If it's not, and again, I've read that paper in your book 3 or 4 times, and after ChatGPTing the whole thing, I go like, this is not observed. This is
let's leave this discussion to the end, I suggest. So
no, I'm done. But thank you.
But what I want to just comment this before we go forward is that somehow this whole issue shows that very often experimental measurements are not taken seriously these days. So the reason why you see that in the ChatGPT, because people tend not to interpret the Compton scattering measurements as giving back a real physical value according to Klein-Nishina formula. And to me, that's why I said about what physics means in the beginning. To me, the meaning of physics is that we make experimental measurements, and then we base our theory on direct interpretation of experimental measurements. For some other people, maybe they don't care about experimental measurements. They like to imagine things. That's fine. They have a different idea of physics. But here, our idea is to really take seriously what Compton scattering measurement, for example, reveals.
Please allow me just a very short comment. Thomson scattering has a fixed radius, but Klein-Nishina is the cross section is decreasing with the photon energy, so it's not a fixed radius.
Yeah, but in the formula, in the formula you have the photon energy, and the photon energy is an input, but the radius is a fixed parameter. The electron mass and the radius is a fixed parameter in the formula.
Yeah. So it's not just the cross section. It's
not
just R square pi.
No. So the cross section is the output of the formula, but input is this R0. So this is an input of the formula.
Yes.
Okay. Okay, so let's go forward. So we had this idea that half of the electron mass is electric field energy. What happens if we consider the other half to be magnetic field energy? Then we take a current loop and we calculate what is the loop radius at which magnetic field is the half of the electron mass. So we take the charge circulation to be the speed of light, which is the Zitterbewegung phenomenon, and then the magnetic loop formula gives us half of the electron mass when the Zitterbewegung radius is 386 femtometers. And this radius also has a name. This is called the reduced Compton radius. So this has a name because it's not a random number. Now, now this is just a model. Okay, so at least this slide is not a direct measurement, but this model I want you to keep in mind because there is several important points here. So the first important point is that by assigning half of the electron mass to this circular Zitterbewegung topology, you get an idea where electron spin is coming from. So this generates electron spin, and in the formula, the magnetic energy is inversely proportional to the Zitterbewegung radius. So this will be important when we talk about proton and other particles, that the Zitterbewegung radius is inversely proportional to the mass of the particle. So the more heavy particle you have, the smaller its Zitterbewegung radius is, and correspondingly the magnetic moment will be smaller as well. So that's why heavy particle have a lower magnetic moment and the electron has a relatively large magnetic moment. What else that's important to say? Another thing that's important to say is that once we have the mass and the Zitterbewegung radius, we can also calculate the frequency. So the frequency that comes out for this light speed circulation is actually mc squared over the Heisenberg constant, which is known as the de Broglie frequency. So that's also quite satisfying that the model gives us back well-known parameters, such as the de Broglie frequency of the oscillation and the reduced Compton radius of the Zitterbewegung radius. Now, if we want to think what kind of experimental match we could have for the Zitterbewegung radius, we can look again at light scattering, but now in the low energy limit. The low energy limit is the Thomson limit. And in the slow energy Thomson limit, the scattering is described by Thomson scattering formula, and matching experimental measurements to the formula, we get the electron radius that is compatible to this approximately 10 times minus 12 meters reduced Compton radius, which Manfred mentioned before we started the lecture. So the low energy scattering is not just scattering off from the spherical charge of the electron, but it's scattering from this whole Zitterbewegung structure, because the light cannot resolve the internal structure of the electron. It sees the whole Zitterbewegung structure while scattering. So in that sense, we can think that yeah, we have also an experimental support for this particular Zitterbewegung radius that we found from magnetic energy considerations.
May I ask a very short question?
Yes, please.
Yes, the picture is then that your electron is a circular current loop, and this current loop with the size of 2 femtometers, so classic electron radius, rotates in Compton wavelengths in
Yes.
around a point.
Yes, exactly.
Okay, thank you.
Yes, welcome. Okay, so now once we have this reasonable model for the electron, natural question to ask, why can we not apply or try to apply the same model for the proton? And let's do that. Let's see what happens if we take the Compton scattering measurements of the proton, for example, as the face value. And these measurements are much more difficult to do because the required photon energy is in the giga electron volt range. So these are not garage experiments, but nevertheless, this has been done. And you can see here the measurement data of the Compton scattering cross-section of light proton measurement. Now, this is not such a nice curve as in the electron case, because there are interfering processes. These large peaks are the particle production peaks, in particular a pion production peak you can prominently see here. So there are interfering processes, but we are not interested in the interfering processes. We are interested in the actual Compton scattering. So we can match the Klein-Nishina formula at the low energy and high energy parts of the spectrum. And when you do match the Klein-Nishina formula in such a way that it integrates with the experimental data, the spherical charge radius that you get for the proton is 0.0015 femtometer. And this match is actually quite sensitive to the radius, because the spherical radius appears as a square in the Klein-Nishina formula. So if you would take a slightly larger spherical charge radius, for example, 0.005 femtometer, which is with the red color here, you can see that in that case, we would exceed the experimental data both in the low end and high end part of the spectrum. So the proton spherical charge radius certainly must be smaller than this red value. All right, so in that sense, we are in a quite good situation that we have a nice experimental measurement that shows us that the proton's spherical charge radius is this tiny 0.0015 femtometer approximately. So it's on the order of 10 to the minus 18 meters. The other types of measurement that we can do about the proton is to measure the mean Zitterbewegung radius. And in the literature, these measurements are being referred to as the proton charge radius measurement. So when you hear in the literature proton charge radius measurement, that gives you this 0.84 femtometers, that's the current co-data value, then think of the mean Zitterbewegung radius of the proton. All right, so these are interesting data, and let's see whether we can apply or interpret this data in the same way as in the electron case. So we have been studying these questions with my co-authors, and we wrote the book called The Protons and Neutrons Internal Structures, where the main goal is to apply the same type of model as the electron for the proton case. And what we found is that we cannot directly apply the same circular Zitterbewegung model, but we have to do a topology change. The smallest change where we get a match is to model the proton as a toroidal Zitterbewegung particle. So once we use the toroidal Zitterbewegung topology, then using just the proton mass as input parameters, we get a quite nice match with various proton values. So the first, which is the most simple, is to calculate the spherical charge radius. So we do it the same way as in the electron case. We apply half of the proton mass to be electric field energy. So it's 400 something mega electron volts, and you calculate how small the radius has to be to give you half of the proton mass. And amazingly, you get 0.0015 femtometers. So in this sense, our electron-like proton model gives us matching results with the Compton scattering. And the reason why I want to emphasize it is that in this way, Compton scattering shows that half of the proton mass is electric field energy. So if you run across some models where they do not assign half of the proton mass to electric field energy, there is a high probability that they are doing something that's in the end not compatible with Compton scattering experimental data. We can also calculate with a toroidal model the Zitterbewegung radius, and there are two radii in this case, the poloidal one, that's the smaller radius, and the toroidal one, that's the big radius. And I cannot in this lecture explain the details of the calculation because we focus on experimental data, but you can find the details in the book. And interestingly, the toroidal radius comes out to be 0.83 femtometers, and that is 99% the same as the mean Zitterbewegung radius of the proton. So we have an experimental match here as well. And the proton's dipole magnetic moment comes out to be 2.9 nuclear magnetons. By definition, a nuclear magneton is the magnetic moment of an energetic positron who has the relativistic mass of the proton mass. So if you observe a positron from a very highly boosted reference frame, where its relativistic mass becomes the proton mass, then the positron's magnetic moment is 1 nuclear magneton. And here we have approximately 3 times higher. And the reason for the higher magnetic moment is because you have only part of the magnetic energy in toroidal direction and the other part in poloidal direction. And you can remember, if you look up the magnetic moment formula, that it's inversely proportional to particle mass. So if you have a smaller fraction of a magnetic mass in a given direction, then you have correspondingly a larger magnetic moment. Okay, the other thing that is directly coming out of this model is the presence of toroidal magnetic moment. Because we have a toroidal topology, we do have a toroidal magnetic moment. Another word for it in the literature is anapole magnetic moment. So anapole and toroidal are synonyms. And there have been experimental measurements of nucleon's anapole magnetic moment. So this is also matching with experiments. So that's quite encouraging that applying the same model as the electron case, but with toroidal topology, we have a number of good matches between experiments and model prediction, and just using the proton mass as input parameter. Now, since this model restores the proton as an elementary particle, it applies that the proton-neutron difference is the presence or absence of a negative elementary charge. So in other words, the model directly predicts that the neutron is in the end a proton plus a negative elementary charge. In the context of this presentation, I will call this negative elementary charge as a nuclear electron. And question is, do we actually have any experimental data that somehow supports the presence of nuclear electrons, or does tell us something about their properties? So the nuclear electron is somehow a heavy electron, in quotes, because when the neutron decays, then it decays into a normal light electron. So we can make a comparison to the muon, because the muon is the best studied heavy electron. So what kind of processes we know about the muon? We know the muon decay process. So when the muon decays into electron, then the difference between muon and electron mass is radiated as neutrino. So then analogously, if the nuclear electron decays into electron, the mass difference will be radiated as neutrino. And
actually, may I interrupt for a moment?
yes,
If the muon decays, then you get two neutrinos, an electron neutrino and a muon neutrino.
yes.
Yeah, not one neutrino. But you get two
Well, this is a simplification. So yeah, sorry, I was not very precise here, but this is now just to get you the context. And you are right, that we can look at it more detailed, but for our purposes, I want to just get the concepts. So in this case, then the nuclear electrons decay produces an electron and a neutrino. So that's just analogous to the muon case. And that's indeed what we observe in the neutron decay. So that then we can imagine neutron decay being the nuclear electron decay. Another type of process that we can observe with the muon is its quantum mechanical state change. And one particularly interesting quantum mechanical state change is when you have a free muon and it goes into a bound muon state. So when the free muon binds together with the proton, then it produces a muonic hydrogen, and the binding energy is radiated as a gamma radiation. Because this is a quantum mechanical state change, the binding with a proton produces a single frequency transversal radiation. That's characteristic of a quantum mechanical state change. And then by exact analogy to this process, we can look for processes where the nuclear electron binds together with a proton, forming a neutron, and the binding energy must be radiated as a gamma radiation because it's just a quantum mechanical state change of the nuclear electron. So based on this direct analogy, what we will be doing is we will be looking for gamma radiation signatures of this kind of nuclear electron capture process. Now we can generalize the process by not only considering a proton, but considering any kind of isotope. So if you have a nuclear electron that's captured by some isotope, let's say charge Z, then after capture, you get a isotope with a charge Z minus one less. And as mentioned before, the binding energy is radiated as a single frequency gamma radiation. Now you can go from isotope charge Z to isotope charge Z minus one also by electron capture route. So in that case, you have the electron mass plus the isotope mass adding up, and they produce this new isotope with charge Z minus one, plus you have electron capture energy that is involved. In most cases, this is negative because by definition, for a stable isotope, for it to be stable, electron capture energy must be a negative value. So, but this electron capture energy has been very precisely measured. So these are well-known data which you can look up from nuclear data tables. Now, if you compare these two equations that I have here, you have the same input and output isotopes with same masses. And what we can do is just subtract these two equations. And after we subtract and rearrange these equations, what we find is that we have an expression for the nuclear electron mass. So the nuclear electron mass is exactly equal to the electron mass plus the binding energy that we can measure minus the electron capture energy that has been already measured. So if we observe this gamma energy that corresponds to such a process, then it means that we can directly calculate the nuclear electron mass. And this formula is very important. So I would like you to remember this, because in the next slides, we will apply it in a few different cases, right? So this formula is the nuclear electron mass measurement formula and we can derive the nuclear electron mass by measuring its radiated binding energy and by knowing the corresponding electron capture energy. Do you have any questions to this formula before we go forward? Okay, I hope that silence means all clear. So let's go forward.
Maybe may I ask?
Yes,
I
please.
still don't understand the first question. So this is a neutron. You say a neutron, or what is the example?
It can be actually any isotope. So I first gave the example of a neutron, but the nuclear electron can be captured by other isotopes as well. For example, by a nitrogen
This
or
is
by something else.
this is
So
electron capture usually.
yeah. So it can be any isotope.
But
If
the
you
second
have a nuclear electron captured by a proton, then it's z equals 1, and then in the output you have z minus 1 equals 0.
So I don't understand the first and the difference between first and second equation. Both is electron capture.
Yeah. So the first one is nuclear electron capture. So we have
Nuclear electron.
our hypothetical
This
nuclear
is
electron
the electron
particle.
of a neutron. This is the electron of a neutron.
Yeah, exactly. So, but it can be a free particle as well. So what I'm saying is that we normally observe nuclear electron inside a neutron, but the question is, can it be a free particle? So my discussion, and I'm sorry I was not clear on the assumption. So the assumption going here is that at least for a short time, the nuclear electron can exist as a free particle, as a heavy electron, and it decays quickly, otherwise we would see it flying around. So as a free particle, it quickly decays, but at least for a short time it exists, and then it can be captured by some isotope, and it turns into another isotope. Yeah, so if it's captured by a proton, for example, it turns into a neutron. If it's captured by a nitrogen, it turns into a carbon. Is that does this clarify what the first equation means?
Yeah, I don't know what you mean with the free neutron, the free electron, this En electron.
So
It could be, of course, that you have a proton which scatters at the nucleus, a neutron which is scattering at the nucleus and makes a transition to a proton, and yeah, somehow the electron is shifted to the nucleus.
Yes. So think about it, very, very simple terms, So you have here in the first equation, the hypothesis, first equation reflects the hypothesis that this nuclear electron, which is a type of heavy electron, exists as a free particle at least for a short time. So then it has a mass. So
Yeah.
if the nuclear electron, the heavy electron, is captured by some isotope, it can be a proton, for example, then it turns into another isotope, for example, a neutron. But if the nuclear electron is captured by a nitrogen, it turns into a carbon. And in any case, the binding energy is radiated as a gamma radiation. And in the
It's
case
some
of electron
electron
capture, you can have a proton capturing an energetic electron and then turning neutron that way. And in that case, you have the electron capture energy that is required to compensate the mass difference.
Thanks.
Andras, I don't understand the transmutation. Can you go slowly through that again for me, please?
Yes. Yeah. So
What
so
is
think
Z? Z is the charge.
Z is
What
the charge of the isotope. M is the
Okay.
mass of the isotope. Z is the charge.
Mhm.
So if you absorb a negative elementary charge, your isotope charge will be 1 less,
Yes.
right? So if a proton absorbs a negative elementary charge, it will have a 0 charge as in a neutron. If as I give this example, if a nitrogen absorbs a negative elementary charge, it will have 1 less charge, so it will be a carbon.
But its mass is not like the mass of the proton. Where do you say this transmutation? So nitrogen is mass.
yeah, there is a mass difference. So there is a mass difference that if you take a nitrogen example, so you have nitrogen 14, right? It has a mass. Then it turns into carbon 14. So carbon 14 has a slightly different mass. So there is a different mass, but but the beauty is that we don't have to care here about the isotope masses, because the first case we have the nuclear electron capture. The second case we compare it to electron capture, and whether you talk about electron capture or heavy electron capture, you have the same isotope masses involved. So we can just subtract. So you can just subtract these.
But talk to me like I'm a 3-year-old, because I am a 3-year-old here.
Yeah, we are all children. It's okay.
Yes, when I have a nitrogen, and I have this, I'm capturing this free electron, which then becomes a nuclear electron in your model.
Okay.
I have
in the second case, yeah, nitrogen captures free electron. It's here.
Okay. And then there's the EEC, which is the
Electron
capture energy, and that's what we radiate. So
no, the electron capture energy is what we measure. So I wrote it here in the end. The electron capture energy can be either positive or negative. So if you have an unstable isotope which wants to capture electrons, then you have the electron capture energy that is positive here. In most cases, if you talk about a stable isotope, then the reason it's stable is because electron capture energy is negative. So it means that you have a negative energy here, and negative energy here means that you have to have energetic electron. So for example, for taking a proton case, it's electron capture energy is minus 780 something kilo electron volt. So that minus value means that the electron must have at least 700 something kilo electron volt energy to be captured by a proton.
Okay, so the second equation describes this capture of an electron, and the EC is the assumed energy.
It's measured. It's measured. So
that's measured.
Exactly. For every isotope, this electron capture energy has been very precisely measured. So that's we're very lucky to have that experimental data that nuclear experimentalists have been very precisely measuring how energetic that electron has to be willing to be captured by.
That makes sense. That makes sense. And so the E gamma in the first refers to an energy of a radiation that we observe differently.
Yeah. So that's something which you do not find in the data tables. The reason why you don't find the E gamma, because this first process has not been studied. So we will study it in the following slides, but in the literature it has not been studied, so you do not find E gamma. But I will show you in the following slides some experiments where we will measure E gamma, and the EEC has been studied in the literature. And you put these equations together, then the point is, once you know E gamma and EEC, then you can exactly determine the nuclear electron mass from these energy values.
So EEC is observed, E gamma is hypothetical.
Yes,
ME
hypothetical, but I will show you experimental measurements for it. Yes.
ME is observed, and
yes.
that's
yes.
But yes. the first experiment is, of course, as you mentioned, nitrogen 14, which is changed to carbon 14.
Yes.
Which then makes a beta decay.
Yes, exactly. Yeah. So this is why it is in red square, because it's one of the most important formulas in the presentation, because we will interpret the experimental data I will show in the following slides according to this formula. Okay, so thank you for the clarifying questions. And now that we understand the meaning of this formula, let's go to experiments and see how we can apply it. So the first experiment that I will look at is an experiment taken from literature. Here is the reference on the bottom. It's an experiment from 2004 by the Focardi group. So what they did, they had a nickel rod that was subjected to hot hydrogen flow. And the experimental details are given in this article. And then they observed some nuclear phenomena in this simple system. Firstly, they observed detection of neutrons. So if you measure neutron emission, it's a signature that something nuclear is happening. And the other thing they observed is the appearance of a 661.5 kiloelectron volt gamma peak. And here you can see their measurement of their gamma peak with a high resolution gamma spectrometer. And this gamma peak diminishes with time, but quite slowly, as you can see here. And the authors could not explain this gamma peak. They did not know why it appeared, what it is. If you look at the isotope table, the only radioactive isotope that has gamma peak at this value is cesium-137, but they carefully pointed out that they do not have in the laboratory any cesium-137, so they emphasized it's not a contamination from that cesium isotope, and also the half-life that you can see here going down is very different than the cesium isotope's half-life. One of the co-authors of our book has been present during this experiment, so he can vouch for this experimental data really being there, because he saw the instrument giving this gamma peak.
You explained it as a decay, some decay, but what is decay?
Yeah, decay or something else. So now what we think of, what if this gamma peak is that kind of binding of the nuclear electrons?
I don't understand. How do you start the process? How do you start the process? Of course, I know in cesium-137 that it decays. It's
yeah, but it's not present here. So yeah, so it's not present here. Yeah, right. So this cannot be cesium because they did not have that in the lab. So
yes.
what they had is nickel and hydrogen. So,
but what is the start time?
Sorry?
When the process starts? When you insert the H2, when you insert hydrogen?
Yeah. After the hot hydrogen flow, sometime after that, they had this process starting.
So, and if you continue with your hydrogen flow, then after some time, there's no decay anymore.
Yeah. So this was a very long-term experiment. So you can see here that they have been running this for over 1 month.
So you have a hydrogen flow. So for 1 month you see a peak, and then it vanishes.
Yeah. Then it eventually vanishes. Yeah. So what you have here in terms of isotopes is hydrogen and nickel. So presence of neutrons is perhaps you have nuclear electron capture by protons, and that gives the inspiration to ask that does this gamma peak correspond to nuclear electron capture by nickel-58? The reason I look at nickel-58 because nickel-58 is the lowest mass nickel isotope, and it is capturing nuclear electrons and electrons most easily. So if you have electron capture or nuclear electron capture, it most easily happens with the nickel-58 isotope. So let's consider the question whether this gamma peak could correspond to this hypothetical nuclear electron capture. And then in that case, the 661 kiloelectron volt is the binding energy that has been radiated. So if we consider that hypothesis and we apply the formula, we put in to the previously discussed formula, electron mass plus this binding energy that's radiated minus the electron capture energy that is known from literature. And then you can see that the nuclear electron mass comes out to be 1,554 kiloelectron volts. approximately 3 times the electron mass. So if this gamma peak corresponds indeed to the nuclear electron captured by nickel-58, then it means that the mass of nuclear electron must be exactly this value, 1,554. Now this is one interpretation of one measurement of the literature, but to have any confidence, we need other type of experiments that give similar gamma peaks. So let's look at other experiments, keeping in mind this mass value that we obtained. So the next experiment has been done by my co-authors, and they did artificial lightning in the laboratory. So they had a 20 kilovolt spark discharge, and there was water moisture going across the spark gap. So it's like a lightning in the humidified environment. And the inspiration for this experiment was the observation that lightnings do produce neutrons. So there is quite a number of studies, and you can see here one examples that document the fact that during lightnings there is some neutron production, so there is some nuclear phenomenon. And I think at least one of these studies they also did replicate it in the laboratory. Okay, so since we know that there are neutrons in the lightning, if you make artificial lightning, then perhaps we can see some nuclear process. And to monitor for nuclear process, the gamma spectrum was observed with this sodium iodide detector, and the whole setup was in a lead shielded box. So what we observed with the co-authors is the appearance of approximately 260 kiloelectron volt gamma peak that you can see here. And you can see by looking at the bottom left that the shielding, high quality shielding has been essential, because the green background is what is measured without shielding. It would make the signal to noise ratio very bad, but with the shielding you have a very good signal to noise ratio, and this appearing gamma peak is very statistically significant. Okay, so the sodium iodide detector is not as precise as in the previous experiment, but by fitting the Gaussian curve, the error can be estimated. So the middle point is 259.6 kiloelectron volt, and the deviation is plus or minus 2 kiloelectron volts by the Gaussian curve fitting. Also, what we did is to run this experiment in the oscilloscope mode, and in that case, the spark discharge signature can be seen here. And there was in the oscilloscope also an RF antenna signal displayed. So you can see the coincident signal between the sodium iodide detector and the RF antenna. So this is the spark part. And then shortly after the spark, you have the gamma signal, and that is shown here. So there is a time coincidence between the spark discharge and the gamma signal. So the two are directly related. One causes the other. Okay, now in this experiment, the isotope that is most capable of nuclear electron capture is a proton, because you have water moisture in the air. And so we assume that for the proton, this 259.6 kiloelectron volt gamma peak is the radiated binding energy. And we put into our formula the well-known proton electron capture energy. And then the nuclear electron mass comes out to 1,553 plus or minus 2 kiloelectron volts. So this is a quite nice result, because we have a completely different setup as before, but we get the same nuclear electron mass. So this now gives us some confidence that, yeah, these gamma peaks could be indeed the binding energy of the nuclear electron capture. Now, to be even more sure, let's look at the third experiment. So this is an experiment which I did with the help of a thorium solution. So here you have on the bottom left the illustration of the thorium decay chain. So thorium decays via evaporation of 5-6 mega electron volt alpha particles. So it's a very handy tabletop accelerator experiment, we can say. And the hypothesis was that perhaps these energetic alpha particles could knock out nuclear electrons from the thorium nucleus, either by direct collision or by Compton scattering of the high energy breaking radiation. So if you knock out a nuclear electron from a thorium nucleus, then you have a uranium-232 nucleus. In case of one electron knockout, the remaining isotope quickly goes into uranium-232, or in case of two electron knockout, you have directly this process. So in either one or two electron knockout case, you go to uranium-232. And that is a nice isotope to have because it has a characteristic gamma signature. The uranium-232 decay produces a 57.8 kilo-electron volt gamma line. And when we looked at the gamma spectrum of a thorium solution with a high-resolution spectrometer, we indeed clearly see this 57.8 kilo-electron volt peak. So
shouldn't be the intermediate state between thorium and uranium, productinium?
Yeah, but the intermediate state is short lived, so we don't care about that.
It's not nucleus, and
it quite quickly goes into uranium-232, and uranium-232 has this characteristic peak. It has a 70-year half-life. So okay, so this is nice that we can see that there is indeed a uranium-232 production that goes this way. So the literature data that you see on the thorium decay chain can be in fact complemented by this pass via U-232 that also happens with some probability. So this you don't find in the literature, but we could directly measure that this branch happens as well. So this is nice that we have this branch because it means that you have some negative charges that are knocked out from thorium, and we can then with reasonable certainty believe that there are nuclear electrons that are being knocked out, and we can look for their subsequent capture. So to get the experiment that measures the effect of their capture, I created two types of thorium nitrate solutions. In one case, I dissolved thorium nitrate in concentrated ammonium nitrate solution. So this concentrated solution has a lot of positively charged ammonium cations. In the other case, I dissolved thorium nitrate without any of this ammonium nitrate salt. And the gamma spectrum that we obtain is illustrated by is shown in this measurement with the red curve in the case that you have ammonium cations, and with the yellow curve when you do not have them. So I show you this part between 872 and 890 kilo-electron volt. That is the interesting part because all the rest of the gamma spectrum was exactly the same. But here in this part, you have a new gamma peak appearing, and this gamma peak you only see in case of the ammonium cations presence. You see also other peaks. These other peaks are corresponding to the actinium gamma lines. These are well known in the literature. Okay, so
do you have some numbers for this transition?
Sorry?
Do you have some numbers for this transition from thorium to uranium? What's the transition rate? Can you measure transition rate?
Yeah, I do not know. Well, you could, yeah, I guess from the comparing this gamma peak to other gamma peaks, you could calculate the probability. I did not calculate the probability, but it can be done by comparing the amplitude of the gamma peaks.
Thorium and uranium may have different chemical properties. So you could wash thorium and remove uranium first, and then see if it's
Yeah, but it does not. No, in this very small concentration, probably you cannot, because you can separate them if you have a high enough concentration. But the point is that the uranium-232 has this characteristic gamma line, and we see the characteristic gamma line, and it's not present in the thorium decay chain. So this is not anything we normally see in the thorium, in the rest of the thorium.
But it could be contaminated. Thorium could be contaminated with a little uranium.
No, because this is not a natural isotope of uranium. So in case of uranium, you have the uranium-235 and 238 isotopes,
Yeah.
but they do not have this gamma line. This only
Okay.
uranium-232 has it.
Yes.
Okay, so yeah, the only reason why we care about this, because it supports our hypothesis that we have nuclear electrons being knocked out. Okay, and so now by comparing the gamma spectrum with and without ammonium cations, we see that the only difference is this peak appearing at 886.6 kiloelectron volt mean energy in case you have ammonium cations. So ammonium cation is a positively charged cation that has a nitrogen in the center, and that's why I assign this as the nuclear electron capture by the nitrogen-14 isotope. And fortunately, I had a good fortune to have access to this high-resolution gamma spectrometer that gives this very precise energy values. Okay, so now we have the gamma energy that corresponds to nitrogen-14 capture. We can look up the corresponding electron capture energy that you see here and apply our formula, and the nuclear electron mass that we get is 1,554 kiloelectron volt, so exactly the same as before. So now we have 3 different measurements, very different techniques. Each one gives you a gamma signature that leads to exactly the same nuclear electron mass value. So I think this is already starting to add up to a quite good evidence that this what we see here on the screen is in fact the precise nuclear electron mass. Okay, now I showed you in this thorium case that there has been some kind of a knocking out of nuclear electrons from a heavy nucleus. I looked in the literature for similar data. So question was, can there be a Compton scattering of nuclear electrons out from an existing nucleus? And here is an article that I found where I saw very nice data that directly gives this kind of reaction. So in this experiment, they had a strontium based material that they subjected to very high energy gamma radiation up to 62 mega electron volts. So after subjecting strontium to this gamma radiation for some time, then they took the material and looked with the gamma spectrometer what kind of lines they have. And here on the slide, you can see an assignment of these different gamma energies. The main point is that they saw the ytterbium-88 isotope appearing and the ytterbium-86 isotope appearing. And the way you get from strontium to ytterbium is by knocking out a negative charge. So it means that this reaction indeed does happen in nature, that a high energy gamma radiation knocks out negative charges from nuclei, and these I describe as the knocking out of nuclear electrons. So that's another experimental evidence you can consider for the existing of nuclear electrons, that a Compton scattering process knocks them out from some nuclei. So if you have this Compton scattering process, then the question is, can we apply our good friend, the Klein-Nishina formula, to describe the actual cross-section of the process? And I did this exercise for the example of deuterium photodissociation. So the deuterium photodissociation cross-section has been measured quite precisely over a very wide energy range, even going up to 100 megaelectron volts. But when they measure the cross-section, they measure it by proton counting. And the proton counting always assumes that there is a proton-neutron dissociation. However, in case of a Compton scattering process, if you kick out a nuclear electron, then what you get is two protons, right? You take a deuteron, which is modeled as a proton plus neutron. You Compton scatter out a nuclear electron, you're left with two protons. So to characterize the Compton scattering process, then you have to take the half of the proton counting rate. And this dark blue line is the half of the nuclear counting rate. Okay, and so then what I did is that I applied the Klein-Nishina formula with different types of masses of the nuclear electron. And you can see that you have a convergence between experimental data and Klein-Nishina formula at approximately 1.5 megaelectron volt. If you take the nuclear electron mass to be a lower value, then you have underestimation. Higher value, you have an overestimation, and you have a good convergence with the 1.5 megaelectron volt that we have been actually measuring in the previous slides. So this is quite satisfactory because it shows that the high energy photodissociation is in the end nothing else than the Compton scattering process of nuclear electrons that is precisely described by the Klein-Nishina formula. In the low energy regime, you have the other process. The other process is the so-called photoelectric effect. So if you consider the difference between the Klein-Nishina formula, the orange curve, and the experimental curve, then this difference is the photoelectric effect that is dominant in the low energy regime. So I think this is quite nice that we can understand photodissociation better, and by knowing the exact value of the photoelectric effect, we can then look for models where the calculated photoelectric effect actually matches the experimental data. Okay, so now I think we can summarize what we learned so far about the nuclear electron. So the existence of the nuclear electron is inspired by proton theory considerations. Experiments show that the nuclear electron mass is precisely 1,554 kiloelectron volt. Nuclear beta decay is the nuclear electrons decay into an electron, ordinary electron, and the nuclear electron is short-lived as a free particle, but is stabilized by a high nuclear binding energy, which you find in heavier isotopes and in deuterium as a simplest isotope that stabilizes it. I have shown you 3 examples of these gamma peaks, but obviously you can think of different experiments. So if anybody is skeptical, you can validate the model by doing other experiments, searching for more types of gamma peaks and seeing if you get the same mass or different mass. So this is quite nice result if this interpretation is correct, because then we can understand what stable matter comprises. Stable matter comprises electrons, protons, and nuclear electrons. So we have found the 3 main constituents of stable matter. Now when I discussed this model with other physicists, which I did a few times before, you know, not everyone is happy, or let's say most people are not happy to see this kind of model. And these are the three main questions that have been coming up in past discussions. So we are interested in counter evidences and counter arguments. So let's look at the main questions. First question is, what about Heisenberg uncertainty? This comes up most often. This is based on the idea that if you have a relatively light particle, such as a nuclear electron or a quark, then the Heisenberg uncertainty is huge. So then it would not be able to be staying in the femtometer scale neutron. So we will address this question on the next slide. I will explain you my thinking relating to Heisenberg uncertainty. In the quark case, you also have a low mass, but they prefer not to talk about Heisenberg uncertainty because the quarks get a golden pass from all the questions, all the critical questions. Then the other question, this has been historically coming up. The question is, wouldn't the photoelectric effect kick out a nuclear electron from a deuteron rather than splitting it into a proton plus neutron? And the reason why this is an important question is that this has been coming up in the very pioneering age of nuclear science in the 1930s, 1940s. So when the neutron was discovered, then the first idea, a natural idea, was to model the neutron as a very tight binding between the proton and some kind of electron-like particle. So in fact, Heisenberg and some other famous scientists have been proponents of that model. And the reason why at that time the concept of a nuclear electron was rejected is that scientists saw that, okay, if we have a nuclear electron and we subject it to a gamma ray, then the gamma ray will preferentially ionize away nuclear electron, and we would see electrons being emitted from a deuteron as it splits, somehow analogy to how electron is kicked out from a hydrogen upon photodissociation. So they applied a direct analogy of a molecular hydrogen theory. And when they did the experiment in that low energy regime, then what was seen is that in the 2 to 5 mega electron volt range, the deuteron photodissociates into proton and neutron and does not kick out any electron. So then this was seen as a counter evidence to the existence of nuclear electron, but the actual calculation was not done. And today we can do better than that because we have computers, which they did not really have in 1930s and 40s, and we can build some kind of a toy model of a deuteron, and we can do actual calculation of the photoelectric effect and see whether the photoelectric effect kicks out a nuclear electron or splits it into proton plus neutron. And this calculation we have done. So in the book, you can find the outline of how to do this calculation. Basically, those people who are experts with quantum field theory calculations can do this calculation easily. And when you do this calculation, then the result shows that the historic assumption was wrong because the photoelectric effect preferentially splits the deuteron into proton plus neutron, exactly what is observed in the experiment. And the reason why nuclear electron ionization is not preferred is because of the associated low density of states. So the theory is actually supporting the experiment here. The third question that I have seen as a counter argument is that the neutron is considered as a fermion, and the proton is also considered to be as a fermion, but a proton plus nuclear electron should be considered as a boson because two fermions combine into a boson. And that was seen as some kind of a contradiction with our nuclear electron model. And now this is actually quite a difficult topic to discuss because properly discussing particle statistics is a lengthy subject. So I give you here just some ideas to think about. When you think about superconductivity, is superconductivity the Bose-Einstein condensation of electrons or not? Electrons are fermions, but if they Bose-Einstein condense, then they bosons under some circumstances.
Okay,
Similarly,
I can answer to that. So
okay.
superconductivity is first stage of Bose-Einstein condensation. However, electrons are charged, so at short distance they repel. So this is like non-full Bose-Einstein condensation when electrons create a quasi-bosons, Cooper pairs. So that's what I can say.
Yeah, but this your answer exactly shows that whether electrons behave as fermions or bosons depends on the circumstances. So it's not just an a priori rigid rule that we have to apply. And similar with the helium-3 superfluidity. Helium-3 superfluidity, which is experimentally observed, is a Bose-Einstein condensation of helium-3, which is fermion. So it means that we have to look at the actual environmental conditions, and we cannot just a priori do these categories. So that's why one should not reject the nuclear electron concept based on the boson versus fermion classification. And if somebody is interested in this topic of electron statistics, we recently published a book on high temperature superconductivity. Here you can see the title, and that contains a discussion of the electron statistics topic. Okay, so these are the three main counterarguments. If you have other ideas that are counterarguments, we can talk about them in the discussion section, but I would like to address Heisenberg uncertainty here. Now, to understand Heisenberg uncertainty, let's start from the concept of the quantum mechanical wave function. So you can consider the quantum mechanical wave as a wave that appears under the Lorentz transformation of a stationary electron. So if you have a stationary electron, its wave function is just flat, but it has the internal Zitterbewegung, which is a time-wise oscillation. Right? We know from the Broglie formula that the Zitterbewegung frequency is electron mass mc squared divided by Planck constant. And I showed you in the previous slide the justification for this de Broglie frequency. Okay, de Broglie frequency is a time-wise oscillation. You look at electron from boosted reference frame. So then the time-wise oscillation has a spatial component, and the time-space mixing matrix is described by this Lorentz transformation matrix. And you can work out the algebra that I seen here. And basically what you find after doing this Lorentz transformation, that the appearing wave number h bar times k is the Lorentz boost factor times rest mass times v. So this is relativistic electron momentum. In other words, h bar times quantum mechanical wave number is the electron momentum. So you can see that this is the basic postulate of quantum mechanics, but we don't have to take it as a postulate because this is simply the Lorentz transformed component we see appearing of the internal Zitterbewegung oscillation. So what this means is that the momentum of electron or any electron-like particle is more fundamentally can be considered as h bar times its wave number. So to consider the Heisenberg uncertainty of the momentum, we can consider the Heisenberg uncertainty of the wave number, which then in turn relates to the Zitterbewegung frequency. So the more high Zitterbewegung frequency you have, the more high this wave number becomes, and then the less the Heisenberg uncertainty is. So we write the Heisenberg uncertainty instead of this usual dx dp formula as dx delta h bar k, where k is the Lorentz transformed component of the Zitterbewegung frequency. So what writing it in this way tells us is that in order to know the particle's Heisenberg uncertainty, we have to know its Zitterbewegung frequency. And so far, this sounds just like semantics, because in the normal case, the Zitterbewegung frequency is just proportional to particle mass. So it's equivalent. These two are equivalent for a free particle, but they are not equivalent for the nuclear electron. So in the nuclear electron, what we are really interested is to understand its Zitterbewegung frequency. And we can understand its Zitterbewegung frequency from magnetic moment considerations. So here we can see the proton's magnetic moment, 2.69 nuclear magnetons, and the neutron's magnetic moment, minus 1.9 nuclear magnetons. And the difference between the proton and nuclear magnetic moment is the contribution of the nuclear electron. This contribution has obviously negative charge because nuclear electron is negatively charged. And the difference comes out to minus 4.7 nuclear magnetons. So compared to the electron, this is a very tiny magnetic moment. And the tiny magnetic moment value means that it has a very high frequency Zitterbewegung. So in fact, if it would be one nuclear magneton, the Zitterbewegung frequency would be the same as the particle which has a proton mass. But here, because we have a larger magnetic moment, it means that the Zitterbewegung frequency is like the proton mass divided by 4.7. That comes out to 200 megaelectron volt. So the nuclear electron, even though its mass is only 1.5 megaelectron volts, it's captured into a very high frequency Zitterbewegung when it's captured by a proton. And because it has a Zitterbewegung frequency like a 200 megaelectron volt particle, the Heisenberg uncertainty is correspondingly much smaller than what you would expect from its mass value. And this is what I see about the nuclear electron mass. Last thing about nuclear electron. Another interesting experiment is to look at the isotopes which are stable in their neutral state but become unstable when they are fully stripped of electrons. And there are a few examples of them. The most well-known example is the dysprosium 163. So this 163 dysprosium is a stable isotope when it's in a normal metallic state or atomic state. But when it is being stripped all of its electrons, then it becomes a beta decaying isotope. So what this experiment shows us is that the stability of nuclear electrons is in fact controlled by the electrostatic potential. And I think that's quite nice supporting evidence as well. That is the electrostatic potential that controls into which energy level it decays, and that controls whether it is stable or not stable. And we can also see that this example of this isotope is in direct contradiction with the idea of emitting 80 gigaelectron volt particles, because if the nuclear beta decay would start by energy momentum violating 80 gigaelectron volt emission, such an emission really would not care about this local electrostatic potential. So you can see that we have a contradiction between experiment and the idea of these virtual particles.
Sorry, this was too fast for me. Can you repeat?
Yeah. So what I showed is that in the case of dysprosium 163 isotope, its nuclear stability is controlled by the electrostatic potential. The reason why you can see it's controlled by electrostatic potential because it's a stable isotope in its natural state, but it becomes beta decaying when it's stripped of its electrons, when it's a highly charged nucleus, right?
Good.
And this idea of the nuclear electron stability being controlled by electrostatic potential is matching our model, but it is in contradiction with a model where the beta decay would start by emission of an 80 gigaelectron volt particle, because emission of an 80 gigaelectron volt particle is violating energy momentum conservation anyway. It would not care at all about small electrostatic potential difference. So that's why.
So what you say is that this boson emits 80 GeV electrons, or?
No. This is what the standard model says. That the standard model says that when you have a beta decaying nucleus, the beta decaying nucleus emits an 80 gigaelectron volt W boson. I'm not saying this. It's the standard model people who say this without any experimental evidence. And I'm saying that, if they were right, this 80 gigaelectron volt W boson particle, it anyway violates energy momentum by a lot. It really would not care about this small electrostatic potential difference. So it would be unstable in any case. Yeah, so this I consider as another experimental evidence that supports our model and disproves the idea of these 80 electron volt particles emitted in the beta decay. Okay. So now we have reviewed all the stable particles that make up electrons and the nucleus, and we can also consider as a curiosity topic unstable particles. So as you know, society has invested billions into high energy accelerator experiments, and then these high energy experiments, they produce unstable mesons that live for a short fraction of a second. So given that we have this high societal investment, okay, let's take a look what we can learn from the outcome of those experiments. The first type of unstable unstable particle that is produced is a muon. The muon mass is about 100 mega electron volt. And you can remember that I showed you quite in the beginning that according to our electron model, the particle mass is inversely proportional to its Zitterbewegung radius, and inverse proportionality to the Zitterbewegung radius also means that the magnetic moment is inversely shrinking to the particle mass. So by measuring the magnetic moment of the muon, we can determine whether it's an electron-like particle or not an electron-like particle. So if the muon has the same internal structure as an electron, then being 200 times heavier, its magnetic moment is 200 times smaller because of the tighter Zitterbewegung. And as a first approximation, that is exactly what experimenters found. So the muon's magnetic moment measurement shrinks in proportion to its mass. So as a first approximation, we can consider the muon to be an energetic electron. And that's also a reasonable model because the muon is always decaying back into an electron. So the muon can be considered as some kind of an unstable high mass electron. Now this model is okay as a first approximation. So the muon is an elementary particle as a first approximation, but there is a small difference in the magnetic moment between electron and muon model. And this is the so-called G factor difference. So this is the anomalous magnetic moment. So if you look at the experimental data and compare the electrons and the muons magnetic moment, this anomalous contribution is slightly different. And this I have shown this table in the previous Zitterbewegung presentation. And this difference is on the order of alpha cube, where alpha is the fine structure constant. And in front of this alpha cube, you have the 8p/3 factor, which is the spherical volume formula. So there is some kind of a geometry difference involved here that makes the electron's G factor have this contribution with a minus and the same contribution with a plus in the muon case. Now, I do not know the explanation for these factors. This is just phenomenological. So, it remains to be seen whether the muon is indeed an elementary particle, or whether this small difference of the magnetic moment means that it is a composite particle of something else as well. So we cannot say 100% sure that it's elementary particle, but at least as a first approximation, we can say that it looks like elementary particle that is electron-like. Now, let's consider the
Andras,
pion. Yes.
Andras, sorry, before you move on, can you explain, like you do in the book, why the alpha square term, the power 2 is 0?
Oh, no, I cannot explain because that's a more lengthy explanation. So that
Okay.
I can do maybe in another lecture why the alpha square term is 0. I cannot summarize it in just one minute. But even if you don't go into the theory, you can see that phenomenologically you can measure difference by the alpha cube factor, right? So if you take the alpha square factor to be 0, then with the alpha cube factor you can measure difference between the normal anomalous magnetic moment, that's the Schwinger formula, and
Right.
the experimental value.
And that's a numerical identification. You say
Yeah. So
it
for the
happens
purposes
to
of this
be-
talk, you can take it as a phenomenological numerical identification.
right. Gotcha.
Okay, now let's now look at the next heavier meson, which is a pion, right? So we go from the electron, then after the electron, the muon was the next well-known meson, and after the muon, the pion is the next well-known meson. And the pion is a short-lived particle, but despite its short half-life, the charged pion can transfer a nuclear electron to a proton. So there is a well-known experiment where charged pions are mixed with protons, and then experimenters has measured that the proton turns into a neutron, and neutral pions appear. So there is some kind of a charge transfer that happens from the pion into the proton. And since we now have the idea that the proton plus nuclear electron is a neutron, so it means that what has been transferred to the proton is a nuclear electron-like particle. So it means that the difference between a neutral pion and a charged pion is the presence of a nuclear electron-like particle. I will call it a pionic electron, E-pi. Now, the binding energy of this pionic electron must be much less than the neutron's binding energy case, right? Because when you have this kind of reaction that occurs spontaneously despite the very short half-life of this particle, it means that this negative charge really wants to be bound to the proton. It doesn't want to be bound to the neutral pion. So this binding energy is much less than the binding energy in the proton case. We have measured the binding energy in the proton case. You remember in the previous slides, it's 0.26 megaelectron volts. So in the pion case, the binding energy is less than 0.26 megaelectron volts, probably much less than that. So we can say that the binding energy is quite negligible compared to the mass of this pionic electron. And with the negligible binding energy, then the mass difference between charged and neutral pion becomes the mass of this pionic electron. And the mass difference between the two particles is 4.5 megaelectron volt. So what we can say is that the charged pion comprises an electron-like particle. We can call it a pionic electron, whose mass is approximately 9 times the electron mass. So you can see here a nice scaling by a factor of 3. So the normal electron has half MeV mass. the nuclear electron has 3 times higher mass, and pionic electron has again 3 times higher mass. And I think that this is something important, this scaling by a factor of 3. So if we want to understand better the structure of particles, we have to somehow understand where this factor of 3 scaling is coming from. Okay, now that we have seen what the charged pion contains, let's consider what the remaining neutral pion contains. Now, the neutron pion can be produced from an electromagnetic wave in the vicinity of a nucleus. And when you have this particle production in the vicinity of a nucleus, then normally you have a pair-antipair production, or particle-antiparticle pair production. Sorry. So the most well-known example of this is the electron-positron pair production, which requires at least 1 MeV photon energy. So in the vicinity of a nucleus, traveling electromagnetic wave then transforms into electron and positron that fly apart, sometimes recombine. You have the same with a muon, but at a much higher energy. And the pion production starts at 140 MeV. And the question arises, because this is an analogous process to particle-antiparticle production, can we consider the pion to be some kind of a particle-antiparticle pair? So if you have a particle-antiparticle pair, before their annihilation, they form a short-lived bound state. So in that sense, maybe the pion is a short-lived bound state of a particle-antiparticle pair. And if that is the case, then upon annihilation, you have the pion mass emitted as 2 photons. And that actually matches experiments, because when neutral pion annihilates, it annihilates into 2 photons. So we have a reasonable anticipation that we have a particle-antiparticle pair inside the neutral pion. But the question is, which kind of particle is inside? Now, to know it definitely, we have to know the binding energy. So we will again consider binding energy gamma measurement. But even before looking at experimental data, we can have an educated guess, because in this mass region of the pion mass, the only similar particle is the muon. So electron has a much lower mass, kaons have a much higher mass. So the best matching mass is actually the muon and anti-muon. So the question is, can we consider the pion to be a short-lived muon-anti-muon pair, which seems to be the most natural interpretation of experimental data? So to definitely answer this question, we have to look at the binding energy being radiated upon the muon-anti-muon combination. And these kind of experiments have been actually performed. So here I list in the literature 2 experiments that have detected unexpected gamma peaks with muon-anti-muon related experiments. And these gammas are not single photon, but diphoton gammas. And that's what you expect in the particle-antiparticle combination, because you have equal mass components that are combined into a bound state. So you have a diphoton radiation from both particle and antiparticle. Now these 2 experiments that I see here, they detect 38 megaelectron volt diphoton radiation. And the first one has seen it in CERN data. And here you can see the peak in the CERN data. And this is subtracted from background, and this is with background. Now, I must say that CERN has stated that the author of this article is just imagining statistically not significant things. So for them, this peak, which is about 2000 events, these 2000 events was just a fluctuation. Okay, but it actually looks to me significant with respect to background. So I don't know why CERN denies their own data. But there was other article by a Russian experimental group that has seen the same kind of d-photon peak in a different experimental setup. And in both cases, the d-photons had a 38 megaelectron volt. So if we now consider this 38 megaelectron volt as the radiated binding energy of the muon anti-muon pair, then it means that we can calculate the mass of the resulting short-lived particle, right? So we have a muon mass, and the muon mass radiates 38 megaelectron volt, and you have to take this 2 times because the muon and anti-muon, they both have the same mass and they both radiate 38 electron volts. So when you do this simple calculation, you see that the resulting neutral particle has 135 megaelectron volt mass. And that is exactly matching the pion mass, the neutral pion mass. So we have, I think, a good reason to believe that the neutral pion is just a short-lived composite of a muon and anti-muon. And that concludes my presentation. So in the summary, we have quite good experimental data about muons and pions that allow us to do an educated guess, actually more than guess, an educated conclusion about their internal structure. So the muon looks like an elementary particle that has the same topology like an electron, and the pion appears to comprise muon-like and nuclear electron-like subparticles. And this conclusion is again very different from standard model, but we come to this conclusion by direct interpretation of experimental data. If you want to come to a different conclusion, you have to read the experimental data in a completely different way or ignore it. And so this is an overview of the highlights from the book, which I mentioned, and further experimental details and the precise calculations of the model you can find in our book, The Protons and Neutrons Internal Structures. So thank you very much for the attention. I hope I did not talk too long. I did not check the time. How long? How are we doing on time?
Yeah, nearly 2 hours. Yeah.
Oh, really?
Yes, thank you very much. Yes, yes.
Oh, I'm very sorry if I talked too long, but I hope you found it interesting.
Yes, very, very interesting. Thank you, thank you. Yeah, so there are many questions also. Who would like to start asking?
I have a question concerning your Zitterbewegung. It's a regular motion. You have a circular motion of your electron.
Yes.
What is the center of this? Why does it rotate so nicely on a circle?
Yeah. So that's a good question. What is in the center? So there is, it somehow rotates around the center of mass of the electron. You can ask the question, what is inside that center of mass? And is the center of mass also oscillating, or is it at a standstill? So
no, my question is concerning this oscillation.
Okay.
So I accept for a moment that you have a sphere which is rotating, which is the electron, and it's rotating around the center. So what is the center?
Yeah. So in the center,
Yes.
in our model, it's only magnetic field. So there is nothing special in the center. It's just magnetic field here.
So you assume a Larmor precession.
No, Larmor precession comes when the electron is inside external magnetic field. So the electron has a Larmor precession inside of the field, but here you do not have a massive particle because the mass is distributed. So the mass of the electron is not in any specific point, but the mass is distributed as electromagnetic field energy. So you have some magnetic energy that's distributed, and electric field energy that's goes into this charged sphere, and in the end, there is a center of mass, which you can somehow calculate, I assume. And if somebody is interested in the model details, then it's possible to calculate the center of mass and the motion of center of mass. In fact, there is a very recent preprint that we published with some co-authors where we calculate what is the center of mass motion.
What is this blue sphere which you have, this small blue sphere? Is this the electron which rotates around? Or
Charge. No, the small
this
blue
is the,
sphere
this
is
the current loop.
the charge.
That's
Yeah,
the
so the
current
electron
loop.
charge is on that sphere.
This is the current loop, this blue
Yeah.
sphere.
No, the blue sphere is where you
Maybe
find
I
the
can-
electron
maybe
charge,
I
and
can help
it
a
is
little.
moving at the speed of light. So the Zitterbewegung is speed of light
Yes, yes.
motion.
But the structure, this small sphere is a current loop, or what is it?
No,
This
no, the
small,
current loop is the large circle.
this is the current loop, what
Yeah,
you call
yeah,
it,
yeah. The large circle is the Zitterbewegung current loop. Yes.
current loop. Yes, and what is the small sphere?
Yeah, the small sphere is the position of the electron charge. So the electron charge is distributed on the small sphere.
And why does this electron charge rotate around something?
Yeah,
let me
because
help.
of the magnetic field. So you have a magnetic
But
field
it's its
that
own magnetic
is a
field.
dipole field, and it's like a Lorentz force. It is a Lorentz force that keeps
But
it.
it's a Lorentz force of its own field, or I don't
Exactly,
understand.
exactly. So the electron charge experiences the Lorentz force coming from its own magnetic field. So it's like a self-interaction field.
Uh, yeah,
There is,
usually-
there is no mass here, yes. That's like we
Yeah, the
have
mass is not in any point. So do
any
not
point.
think
The
that
point is-
electron mass is here or there. The electron mass is distributed electromagnetic field energy, but within that distribution, you can calculate the center of mass. So you can ask, where is the center of mass, and you can actually calculate it, and you can calculate the motion of the center of mass.
But
But
there's
the
nothing
center
there.
of mass is just an abstract point because the factual physical mass is distributed in the electromagnetic field.
But the charge which creates the magnetic field, but how does it look like?
Yeah,
Is
this is the charge. So that this is a self-interaction.
But is it a sphere or what is
The
it?
sphere, yeah, it's the
How do you
sphere.
make a model of this charge? What is your model of this charge?
Sorry, what stabilizes the sphere? Is that
No. We have yes. What is yes?
In the book, there is a model.
Structure and how it's stable.
Yeah. Well, that's the big question that we do not know. So that's the big open question. How does this structure stabilizes itself? And I think that is the big question in Zitterbewegung research, to understand how this topology stabilizes itself. And I think that's Jarek's field of research, to understand how it
Yes,
stabilizes.
to stabilize this field energy inside this charge, we need the charge quantization in Gauss law. So that's the first question. Also, I cannot believe it's so huge circle, and what makes it circle? Where this magnetic field comes from? I cannot see it.
By the way, Andras, can you comment on the fact that the radius between the classical electron and the Zitterbewegung electron, the ratio between the small and the big one, is the alpha 137?
Exactly. So the ratio between this radius of the sphere and the radius of the current loop is exactly the fine structure constant, and that's quite interesting that you see that fine structure constant appearing here as a geometric parameter.
Using the maximal entropy random walk of Jarek, I got this Zitterbewegung just from the random walk. So it's not a regular motion, but I got it from a random walk.
Yeah, but the two maybe are not in contradiction, because I think this is you can there was this Zitterbewegung conference organized by Jarek, and there was Alvaro. Can you help me? What his last name?
Alvaro Gomez.
Alvaro,
Yes. So he's model was to consider a random walk model, and he then derived into the condition of how it is stabilized. So I think there is no contradiction, because it is possible that you start from a random fluctuation that is self-stabilizing itself under some condition. So you can think of it as self-stabilized random process.
I have read Alvaro's papers after the conference. It's very interesting. We had seen in the hydrodynamic walkers, like the Booth and Langevin, the auto-orbit. We were looking for Bell, but we saw the auto-orbit. We saw the auto-orbit by auto-stabilization of the standing wave. This is how I got to Zitterbewegung. And Alvaro basically says, look, we have to take into account the fact that we're relativistic media, so there's a delayed potential. The force is delayed. There's a delay by the propagation of the signal. And this is called a Liénard potential, studied in the 19th century. Not much, because nobody cared. A delayed potential. When you have delayed potential, it's a nonlinear phenomena and all kinds of stabilization that occurs, and very well characterized. And Alvaro characterized the limit cycles, super stable limit cycles. Shows them emergence, shows them structurally stable and generic. They will always emerge in the self-oscillation is the norm, rather than the exception, right?
Yeah.
And he further showed that a elongated shape will lead to this self-oscillation, whereas the perfect spherical shape will not. And he talked about a Hubble bifurcation in between the morphic things. And that's it. That's what Alvaro talks about. And that would happen at the scale where Andras hypothesizes this perfect field at E minus 15 as a charged circulation, which is fine. It's the model. That's it.
Yes, thank you for that comment. And so I think that there are various research approaches that are somehow complementary, and we still have to do work to understand the details and understand the dynamics. So I'm not saying that this is the complete knowledge here. I think Alvaro's work is very interesting, and many others do very interesting work. What I aim here is to do the simplest mapping between experimental data and the electromagnetic model. And this is the simplest topology, is circular Zitterbewegung, where you have a good match between experiment and model. So I have been, in all this presentation, just focusing on a match between experiment and simple model.
Generally, the problem is that such additional time derivation increases the energy. So naively, this configuration should reduce these time derivatives, but it doesn't. So I think it needs some concrete mechanics. How to make it that it does not increase energy, but maybe reduces that there is some preferred frequency. So
yeah. What we found is quantized is the magnetic flux and the angular momentum. So the angular momentum is always quantized to h bar, and magnetic flux is always quantized to h over e, Planck constant over elementary charge. And yeah, that's the question that is still unanswered. What causes precisely the angular momentum quantization and magnetic flux quantization? So as you know from the email discussion, I think these are fundamental questions to answer, where this quantization coming from.
I do not have the impression that magnetic flux is quantized. In the Aharonov form effect, you can have any magnetic flux.
Yeah, I think we had this discussion by email, so I have to be more precise. Magnetic flux is quantized in context of elementary particles internal structure or orbit. So when you talk about an atomic orbit or talk about the internal Zitterbewegung, in these elementary particle context, it's quantized.
So it's somehow like in a superfluid
Yes, exactly. And
superpairs which quantize the magnetic flux.
there came this analogy between the superfluid and elementary particle flux. Yes.
If you have quantization like because of vortex, then if there is time derivative. Our magnetic field is proportional to time. How fast the field rotates is crucial for us, not just quantization. So in your view, for quantized because of vortices, if the magnetic field is different, the speed of rotation of the field. Okay, so I have a different question. So you say that muon and so we found you have found why you have 3 leptons for you have omitted town.
Yeah, you mean why there are not more than 3 leptons?
Exactly, yes.
Yeah, well, it's a it's a question of how do you define a lepton? So let me go back to that. To this one. So is the nuclear electron a lepton? Maybe you can say nuclear electron is a lepton because it decays to a normal electron. Maybe pionic electron is another lepton. So maybe there are more than 3 leptons, and that's what experimental data suggests.
So here we have town. It's heavier. Usually the third lepton is town. So we are saying something different. So pions are very special particles. For example, in colliders, they get mainly pions. They are the main particles created in these collisions, particle collisions.
Yes.
So why there are?
Yeah, that's also a good question. That when you have a proton and antiproton annihilating, then a proton antiproton annihilation, it shoots off 6 or 7 pions and antipions.
Yeah. So also all these colliders, where the proton lead, proton gold, they get mostly pions.
Yeah, that's a good question. I don't know. But to me, it could be that really what is created is muons and anti-muons, and muon anti-muon, it combines into the pion before annihilating. Because
So
if you think, what is between a proton and electron, what mass do you have in the range between proton and electron? Well, you have the muon, somewhere there at 100 mega electron volt. So it could be that it is in fact a lot of muons and anti-muons that are created and they are combined before into
generally they are searching for, they call it true muonium, this muon anti-muon. For electron, we know everything.
Yes.
Positronium, parapositronium. For muon, there are these exotic atoms. And finally, they would like to find this true muonium, but I have just checked, and they were not able to check it experimentally. But you are saying the pions are
Yeah, exactly. So my proposition is that is the neutral pion. That's the true muonium.
Okay.
Yeah, I need to go. I just want to say I love the work. I'm glad to have in any way.
And Mark, how is this calculation with Maciek Tacapiński? You are using the CPS.
We're using CAPD, and now Will Quint of NRS is helping with the precision integrator where CAPD is. So we'll be able to model dynamics of feedback. But it's at a higher level. It's at minus 13 meters, right? Andras is focused on minus 15. I have loved the picture of the positron and electron as the vortex, appearing in a strong flow of electromagnetism. The photon, positron, electron. Anyway, I will thank Herman because I think Herman will want to run a possible experiment, coming out of this to replicate things like that.
Let's see. Okay, so some further questions. So what is you have also nuclei, and so we are saying that you have large nuclei, lots of positive charges, and you gave this this one example that the electrons can stabilize, but generally this is very rare case. So usually lots of positive charges, and why they are not escaping the protons from lead from gold.
This is just one example. Yeah, the reason why protons do not escape is that you have the negative charges that pull them back. So let's understand the deuteron first, because the deuteron is the simplest nucleus. So I here calculated the Compton scattering properties. So maybe we can start by understanding the simplest nucleus, which is deuteron. So you have a proton, and the negative nuclear electron is somehow between them. At least part of the time is between them. So it's the attraction of the negative charge that pulls them together. And well, as you very well know, Jarek, this model is matching the quadrupole electric moment.
Yes, so I believe if you just put the simulation of 2 pluses, 1 minus, 2 heavy pluses, one light minus, that it will follow. But for large nuclei, it's completely hopeless. So imagine some gold nuclei. It can be just without electrons. Gold.
Well, I don't have the answer to this, but I think in general we have to start by understanding the simpler one and building step by step from simpler to more complex. And we can start by trying to understand the neutron structure. So to me it's not quite clear yet exactly how this nuclear electron is captured inside this neutron. So the neutron has a toroidal structure, or a proton has a toroidal structure, and this sphere on which nuclear electron is located, it seems to be fitting into this torus. So it's somehow moving inside this torus. And that could be a geometric coincidence. Maybe it's not a coincidence, but I think we could start by trying to understand the neutron of how exactly the neutron structure is stabilized, at least for a few minutes. So there is many questions still that one has to answer and one can search. Important thing is to start researching in the right direction, not in the wrong direction, in my opinion.
Sure, and so the first question is again, why Gauss law it cannot give half of electron, but only integer multiplicity. That's the first question.
But this I don't have answer. So my intention was not to say that I have all the answers answered. My intention was to show how I think experimental data can be interpreted in most direct way.
Andras, could I depart from the current discussion? There were two things that you said that drew my attention. The one was that you are looking at alternative energy sources. And the second one was your nickel and hot hydrogen data. Now, there was a project in Canada, privately run project under the name of Sapphire, which was a plasma chamber, basically a plasma discharge chamber in low vacuum hydrogen. And these guys destroyed a linear probe of tungsten, and the tungsten completely changed its metallic structure or crystalline structure. And I looked at this, and I basically, during this talk, I also looked at nickel. There is an aspect of the various isotopes which, in terms of energy production, I don't think have ever been thought of or tried to be exploited. For instance, if we take the nickel, we can, let me just get my data here. if we take the nickel 61 isotope, is heavier than per nuclei than what the 60 and 62 isotopes are per nuclei. Therefore, one can envisage a isotope mutation from the 61 isotope into a 60 and a 62 isotope and release energy. And I just did a calculation here that would actually release 2.7 mega electron volts, which is a huge amount of energy. Have you considered this sort of aspects if you, in terms of energy production, if you're looking at alternative energy productions?
I did, various experiments, not this one particular, so I did not consider what you were suggesting. I prefer to answer this question, generally, that in generally, I think if we understand nuclear structures and dynamics, better than before, there will be technological applications, because, in general, a hallmark of a correct and important theory is that the theory gives practical predictions, and practical predictions can be turned into technological applications. So I believe that if, for example, QCD was a correct theory, it would have technological applications, but it does not have. So if we are going on the correct path, then eventually we will have technological applications. But specifically, I do not want now to go into a discussion of what are the future energy technologies going to be, because that's a long and different discussion. So let's leave it as a homework for everyone. But if you want to write me follow-up emails, always welcome to discuss by follow-up emails.
Okay, Andrew, Andras, I will. Another thing with your theory of the nuclear electron, can you explain the progression or nuclear packing to get sort of a general trend to the atomic masses, and why iron should have be the densest atom as such?
Well, that's a good question. So if you look at the radius of the various isotopes versus mass, then you can see that the heavy nuclei, they are built of nucleons that have approximately the proton mass. So the nuclei look like tightly packed protons, basically. So within the structure of tightly packed protons, why the iron is ideal, I did not calculate. I do not have an answer. But what you can notice is the change starting from calcium, because going up to calcium, your preferentially is just alpha particles that are built first into oxygen structures and then into other structures. So you have basically the proton number and neutron number equal up to calcium, because you have alpha particles being added. But this ratio changes starting from calcium, and I think this change of the ratio means that you can have more nuclear electrons being possibly bound starting from calcium. So you have a new type of binding state. So what I think is that there is not only one type of binding that you have in the nucleus, but you can probably have different types of bindings same like in the atomic orbitals, you have S, P, so forth. So you have, one type of binding mechanism in the neutron, then maybe a different type in the alpha particle, and starting from a calcium, above calcium, you have another type of binding that accommodates additional nuclear electrons. So I think that the reason why this is a complicated problem is that there is not only one type of binding. You can start by first understanding the neutron, and that's a good starting point. And maybe second step, understand the alpha particle, and then go forward. But eventually you have to understand multiple types of binding mechanisms to determine out of all of these sums why iron is the optimal.
How do you see the nucleon of heavier atoms? Do you see them as this picture that we see everywhere of marbles sitting together, or do you see it as an onion shell model?
Well, the experimental measurements basically show us marbles sitting together because you have a tightly packed proton. So if you compare the proton radius to the spherical radius of the heavy nuclei, you basically get the tight packing proton model. So you get this tightly packed model. And the question is, does this core shell thing have any validity? In my book, we do have a chapter where we look at signatures of the nuclear electrons' radial oscillation, and actually you can get again quite nice interpretation of experimental data by matching the neutrino spectrum versus considerations of radial oscillation. And I think we have good experimental data that demonstrates the radial oscillation of nuclear electrons. And it is possible that these so-called nuclear shells are various oscillation modes of nuclear electron in the end. I think it's possible.
Just to check, your book is Unified Field Theory and Occam's Razor.
Oh, that's the electron. That's about the electron. So if you want to read our electron model, that's the Unified Field Theory and Occam's Razor. But if you want to read our results about the neutron and proton, that's the protons and neutrons internal structures.
Okay.
So very good questions.
Thank you. It was not quite what you presented, but sort of.
No, but very relevant, because I think it's very good questions, because in the end, the motivation comes from eventually applying the theory, and I think it's very good and needed to have a kind of idea how we will apply the theory in practice in the end. And yeah, I do believe that in the end there will be nuclear energy technology applications of a correct theory.
I'm sure. I'm absolutely sure you're correct in that part.
So fusion, or maybe the proton decay, baryon decay.
Yeah, maybe. So that's something like that could be.
So do you believe the baryon number is conserved ultimately, or always, or not?
Well, I believe. Excuse me. I believe there's a something between a hot and a cold fusion. We know of all the cold fusion experiments with palladium or whatever, but I believe there'd be something else where we'd be looking at isotope mutations to take an isotope which has a high energy and its immediate neighbors of low energy, that you can mutate that higher energy into the two lower energy
So
isotopes.
this kind of changes isotope are standard both for fission and fusion. Yes, so you can do it through beta or beta capture or beta decay. So this is change of energy of isotope is a process inside this both.
It's inside the nucleus. It just needs the right sort of excitation to do it.
Yeah, so in fusion you'd like to fuse, in fission you'd like to get to higher state, which is unstable, yeah.
Yeah, and it could be that both are possible. So it could be that in the end you could have some new approaches to both fusion-like and fission-like processes.
But if the baryon number is not conserved, then could be even better methods like
the proton the proton decay is the ultimate energy source. Unfortunately, we discussed that in the book, that if you have a hypothetical proton decay, most of its energy would be radiated as an energetic neutrino. So, and that's a big technological challenge, that even if you theoretically could achieve proton decay, which is theoretically the highest energy source, how do you capture the neutrinos which carry away its energy?
In Hawking radiation, there are massless by definition. So it could be neutrino in Hawking radiation. So if you take baryons, squeeze them into a black hole, and gather Hawking radiation, then there are no neutrinos.
Yes, but that's a little bit. It's not a little bit, but that's very much advanced technology, right? So you you cannot let's say you cannot do a very simple approach. The problem is that you need something very advanced to capture the neutrinos, and I think that's their main technical issue.
So I'm saying that going through black hole, then you don't need neutrinos. And also, so in standard proton decay is to positron and plus gammas mainly. And neutrino is a tiny fraction of this. I don't think it will be essential neutrino here.
No, we discussed it in the book. So in the book we claim, I don't know if we are 100% correct, but based on the model that we build, the prediction of our model is that the hypothetical proton decay mostly emits neutrino energy.
So what is neutrino in your view?
I have some ideas in the book, but let's say that's a long discussion. That's a long discussion. So
you said that it is electromagnetic.
I do believe that it has an electromagnetic structure. Yes.
So and we had discussion that gammas go at least like 1 centimeter of lead, and neutrinos can go through Earth. So what allows them to travel to Earth?
Yeah, this is why it's a difficult discussion, because I give some ideas in the book which somehow seem to follow from Maxwell's equation, but I do not have a precise answer why they interact so little. So I do think that they have an electromagnetic structure that seems to follow from the particle models, but I do not have a good or precise answer why they interact so little.
So a basic electromagnetic particle is the photon. So what is the difference between photon and your neutrino?
That in the photon there is no scalar field. So in the gaugeless electromagnetism, you can have a scalar field, but in the photon you do not have a scalar field. You only have magnetic and electric fields. But in the case of neutrino, you have a scalar field as well. So that's like an additional degree of freedom you have.
So you are saying that your field is electromagnetic plus some scalar field. Yeah?
That's also part of electromagnetic field. So the scalar field is electromagnetic, but you can only discuss it in the gaugeless electromagnetism theory. So yeah, so you can think of it as spin and isospin. It's really analogous. That the photon has only spin. Neutrino has additional degree of freedom, also isospin. So in that sense, it's somehow similar to the standard model, but we can describe it all as part of electromagnetic field.
So if you add to photon this additional degree of freedom, then it becomes completely stable. Yeah, yes, you are saying.
Yeah. Well, you know, these are long discussions, and these are the big questions that are the open questions. You know, exactly what are the differences between photon and neutrino.
Yeah, I think we need some topological stabilization mechanism again. So
Yeah, it could be right. You're probably right. So that, you know, the topology is fascinating. It has a very big role because the main point here is that the electron-proton main difference is just topology. That electron has circular Zitterbewegung, proton has toroidal. So the topology difference makes a huge difference of seeing an electron versus proton.
So you believe that there are some structures? Do you think there are because of vortex like structures, for example, in QCD? Do you think there are?
Yeah. So this abricos of vortex-like structure is the magnetic flux quantization that we discussed.
Okay, sure. So yeah, so if having this abricos of vortex, just enclose it into a loop.
Exactly.
Could it be a neutrino?
Exactly. It's like that.
For me, it is neutrino, the simplest loop.
Yes. And so we are really thinking the same way on that. Yes.
Yeah. So it is close to electromagnetic, but much more stable because of the topological constraints.
Yes.
And there are three types. Literally, you can get you can perform this loop along one of the three axes, and then you get three types.
Yes.
And also there should be the clock. Again, very similar as for electron, but to make that these three axes rotate through these neutrino oscillations.
Yes. So I think that in the end, once we map these particles to their topological structures, like you are doing, we could have a reasonable map in the end of what is possible, and it will be interesting to see out of possibilities what nature realizes, what not, why not.
Yeah. So to answer this question, the best is this string hadronization. That we assume that there is this one string. You can imagine because of vortex, and it reconnects the kinds of particles, mostly pions, in colliders. So we just need to analyze what is because of vortex can decay into, and you can say that simple loop is neutrino. Then you can get simple loop plus twist. And I think it's pion. Simple loop, like Möbius strip.
Well, you know, that's then again the big question that if the muon is the same as the electron, you know, it looks like similar structure based on magnetic moment. Why is it that the electron forms this positronium where the two charges are quite far away, but the muon forms this pion where the two charges are really close together?
So maybe let me show this one slide. So here, so they believe that this one because of vortex, in collision of two like electron and positron, they form this hot because of vortex, and it decays through reconnection. So the question is what can it decay into, and mostly into pions in practice. So pions, I think. So maybe also neutrino. So neutrino would be the simplest, and the difference between pion and neutrino, you need this twist inside, like this Möbius strip. You cannot avoid these kind of solutions if you consider the because of vortex seriously.
Yeah. So this could be, but the question is, why do you see the pion-like structure forming from muon and anti-muon, but not seeing that, as far as we know, from positron plus electron?
I think this is not so. This is true muonium is something different than pion.
And we have to see the experimental data. So
they try to get it, but they were not
able. Tell me.
Yeah. They are not able to get this true muonium. They only get anti-muon plus electron, for example, and it works well. Yeah. So, but generally, if you believe in because of vortex, then it can perform this kind of constructions. So just loop, but what with twist. Yes. So you need some interpretation for this kind of topological structure. And
Yeah,
I think
so
that
I think that's important work to try to understand what these topological structures look like in terms of electromagnetic field configuration. So that's what I'm interested in. So but I think I have to go soon. So
Sure.
we had a very good session with very good questions. So if there are no other last questions, then I suggest that we conclude the webinar. And thank you very much, Jarek, for organizing it, and thank you for all the audience who has been present and still present.
Thank you for your nice talk.
Thank you very much.
Welcome. Keep in touch.
Andras.
Bye bye. Bye.
Thanks. Okay.